Welcome to the second lecture of Unit 3, Forces Within. This lecture will cover material from Chapter 8, Earthquakes and the Earth's Interior. Now remember, Unit 3, Forces Within, deals with the forces inside the solid Earth that manifest themselves or impact and essentially shape and form the Earth's surface where humans interact with the Earth. The first chapter of Unit 3 dealt with plate tectonics, the driving mechanism for most deep Earth processes and superficial processes that act over geologic timescales. Now, Chapter 8, Earthquakes and Earth's Interior, will discuss one component of a tectonically driven system, and that is the movement of energy through the solid Earth. Earthquakes are quite important when it comes to how humans exist and how humans relate to the solid Earth or to the Earth. Earthquakes can happen without warning in some cases. Sometimes there are hints of warnings, and new research is being conducted every day to try to improve earthquake prediction. But earthquakes can have devastating consequences for societies and cultures and communities. As one of the more recent large magnitude earthquakes that struck near Port-au-Prince, Haiti, several years ago. On a fundamental level, earthquakes are caused by strains that build up and stresses that build up within the surface of the Earth due to tectonic forcing. Earth, or the crust, is a solid material, though it can behave in a brittle fashion, or it can behave in a fluid-like or a deformable fashion. The basic sequence of events that produces earthquakes, or seismicity, start as tectonic motion, acting over tens to hundreds or thousands or even millions of years, moves blocks of crust or exerts force on blocks of crust that are rigidly or semi-rigidly connected to other adjacent blocks of crust that aren't subject to the same forcing. That will build up energy and build up stress in those blocks. Here we have an example of crust that's in an original position. As tectonic forces start to stress and strain this block here, it moves, which causes deformation and strain to build up along this fault boundary, akin to bending a stick. Original stick has no stresses on it, but as you exert stresses on either side, it starts to bend. The same thing happens in the solid Earth and in the crust. At some point, and that can act over tens to hundreds to thousands of years. At some point, that strain and stress reaches a critical point where blocks of crust will actually slip and slide within seconds or a few minutes past each other. This blurred out graphic shows the pace of that movement. And that's akin to the actual cracking of the stick that one has been bending. It's been deforming, and then all of a sudden you have a catastrophic failure along a surface where movement occurs. And then the last stage of that is that when your blocks have already slipped, that strain has been released. And tectonic forces will eventually start to build up again and cause further stress and strain and further earthquakes. And that's, in a nutshell, why earthquakes occur seemingly randomly, but in a predictable location and with predictable intensities. Some terms that earth scientists use to describe and to study earthquakes are shown here on this graphic. The focus of an earthquake is the actual point inside the Earth, whether it's shallow, or deep in the crust, or deep in the deep crust. The focus is the point of actual slippage of the Earth. And that's an earthquake focus. And the term you often hear in news reports of earthquakes is where the epicenter is. The epicenter is the point on the Earth's surface directly above the focus. So the focus is where the release of energy takes place. The epicenter is the point on the Earth's surface closest to that point. and faults are these planes of slippage, along which blocks of crust will slide. Now, at an earthquake focus, the Earth is slipping along a fault, and energy is released. This graphic shows energy being released in all directions. Actually, if you pay particular attention, there's some difference in the length of the arrows, and that's important because energy is not released outwardly from an earthquake focus equally in all directions. In fact, the only thing known to humans that can release energy equally in all directions deep underground is an actual bomb explosion. And in fact, during the Cold War, the period of time between the end of World War II and, say, the late 80s, late 1980s, the major nuclear nations, China, Soviet Union, United States, France, Britain, among others, did significant nuclear bomb testing deep inside the Earth. It was not a really good... People complained vociferously against testing nuclear bombs on the surface and in the atmosphere, but these nations that were developing nuclear arsenals needed to test their bombs, and oftentimes they would test them deep underground. Earth scientists and seismologists in particular were critical in monitoring on the location and the intensity of underground nuclear tests, because the same tools that they use for measuring earthquakes and intensities were directly applicable to monitoring the locations and directions of nuclear bomb blasts. And nuclear bomb blasts that are deep inside the Earth are very, very distinguishable from earthquakes, for the very reason that nuclear bomb blasts blowing outward release energy equally in all directions, or somewhat equally in all directions, whereas earthquakes, there's definitely a bias to the direction of energy release due to the relative motion of the crustal blocks that are causing that earthquake. Earthquakes have various different kinds of energy or waves are released during earthquakes. The two main types of waves that are released in earthquakes are P waves. These are compressional waves. If the illustration is using a slinky, which is basically a coiled spring toy, if you don't know what a slinky is. When you push that slinky, there's a wave of energy that progresses in a straight line through that slinky. That's a compressional wave, or what seismologists call a P wave. Now, an S wave is more of a shaking motion. It's not a compressional wave. It's a back and forth or up and down motion, and it's analogous to a rope with a wave. When you give a rope a little snap, and a wave kind of propagates down that rope. Now, what they show here is particle motion. They illustrate particle motion here in the compressional stage, and particle motion in the S wave stage. And P waves and S waves both exert energy on particles. That is molecules of rock inside the Earth. And what's interesting is that compressional waves, which are pushing through the rock in a sense, travel much, much faster than S waves. Now, very, very close to an earthquake focus, you would find that the S waves and P waves would show up. If you were there standing very, very close to an earthquake, you wouldn't really be able to tell the difference of when one arrived and when another arrived. But if you're very, very far away, the P waves are traveling so much faster that there'll be a gap in time between when the P waves get to your location and the S waves. Now, a third kind of wave, often that is always occurs with earthquakes, is called a surface wave. And that is when the wave energy or the earthquake energy gets to the Earth's surface, it exhibits a rolling motion. And surface waves are actually what cause the most damage in earthquakes. Those are impacting humans the most. To blow up picture of surface waves, and you can see as structural infrastructure starts to take on those waves, eventually it will fail, and that's what really happens with solid human developed infrastructure. Now, a seismograph is a tool that seismologists use to monitor for earthquake occurrence, and also they use to develop location data for earthquakes and intensity. Seismograph is really quite a simple instrument. It's a set of springs that are affixed to the ground. You can see how this plate that the seismograph is affixed on is kind of connected to the bedrock. It can be screwed in or cemented in, or basically just sitting on bedrock. Oftentimes they're in a hole, a deep, deep down hole in the earth, so that surface things, trucks driving by, people walking, doors slamming, don't impact it, that it's really truly picking up waves from deep in the earth. And what it has is a small little pen or a marker that is resting on a coil of paper. And when the earth starts to shake, this arm, which is freely suspended, will move back and forth in proportion to the direction of the shake as well as the amplitude of the shake. This is a real live picture, and you can see these small little lines up here. This drum continuously spins around, either once every 24 hours or once per hour, or whatever the drum is set up to spin. And so each of these lines represent a certain amount of time. It usually gives a little bit of a tick. If you were to blow this up, a little bit of a tick at every hour mark or minute mark or day mark, as it were. But if an earthquake event occurs or a seismic event occurs, all of a sudden you get the appearance of waves on your chart recorder, which is what a seismograph essentially is. This is a representative chart recorder or seismogram of a earthquake arrival, and you can see how the P wave, these compressional waves, travel very, very fast. They get to the seismograph first, and the seismogram records them ahead of the first S wave arrival, which are typically larger amplitude. And then the surface waves come in, which are the really high amplitude stuff that does all the damage. Those are the slowest moving waves. You can see the seismogram here has markers for time. So in this distance we have what? We have our first P wave arriving at this line. If these are all minutes, then we have 1 minute, 2 minutes, 3 minutes, 4 minutes, 5 minutes, 6 minutes before the first S wave arrives. And then 7, 8, 9, 10 before the first surface wave arrives. So here we have a difference between the P and the S of 6 minutes, a 6-minute travel time difference. These are 3 sample seismograms from the same event recorded on 3 different seismograms in different locations. Okay? Here we have a seismogram where the first P wave arrival is at, well, we'll start from this line, will be time 0. 1, 2, 3. P wave arrives at time marker 3 minutes in Nagpur, India, at 2 minutes in Darwin, Australia, and it looks like it's arriving at 1 minute in Paris, France. Although these, I should caution you that what we're going to use this example for is not the absolute time at which they arrive, but the difference in between the P and the S. So let's look at the difference between the P and the S wave arrival from India is 1, 2, 3, 4, 5 minutes. In Australia, it's 1, 2, 3, 4, 5, 6, 7 minutes. And in France, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 and a half minutes before the first S wave. So we've got a 5 minute, a 7 minute, and a 10 and a half minute arrival difference between the P and the S wave. Seismologists can use that difference of those from those 3 stations to figure out a distance from the earthquake location. So the S wave curve is the time at which it takes an S wave to travel through the solid Earth. So it takes an S wave to travel 1,000 kilometers, takes it roughly 4 minutes. An S wave travels 2,000 kilometers, let's find our 2,000, go up to the S wave curve, a little bit under 8 minutes. P waves, as we know, travel much faster. So P wave travels 1,000 kilometers in just over 2 minutes, and it travels 2,000 kilometers in just over 4. Well, the distance between these two, if we know that we have a 5-minute time difference between the P and the S wave, as we do here, 5 minutes, we have a 5-minute time difference between that and that, we can say, well, that earthquake occurred 3,500 kilometers away. If we go to a 7-minute time difference, which is about, well, it looks like it's not even on this chart, but 1, 2, 3, 4, 5, 6, that's only a 6-minute time difference here at 5,000 kilometers. The Australia event was 7 minutes apart. It's not even represented on here, but it's further than 5,000 kilometers if you're following what I'm doing. The way seismologists use this is if they have 3 points, they can calculate a distance from that measurement point to the earthquake. And if you do that with 3 different stations, the way geometry on the solid Earth works, on the spherical Earth, is that the India earthquake, or the India station, recorded it as 3,400 kilometers. The Darwin, using the travel time curves, was 4,900 kilometers, and the Paris, France was 8,200 kilometers. If you find that location, Paris here, Paris, and you draw a circle of 8,200 kilometer diameter around the entire Earth, that circle is right there. If you do the same thing from Darwin, Australia, where that other seismogram was located, and draw a circle of 4,900 kilometers all around the Earth, it will intersect the Paris line, which is orange, in two places. It intersects it right there, and it intersects it right there. So that means that an earthquake happening 4,900 kilometers from Darwin and 8,200 kilometers from Paris could be located here or here. Now you need a third station in order to calculate or to locate an exact location, and that's the India station, 3,400 kilometers. You draw another circle around that. It doesn't intersect with this intersection of the Darwin and the Paris circle, but it does intersect with this one. So that's where the earthquake is located. Using data from 3 seismic stations, one can locate an earthquake on at any point on the Earth's surface. It's a triangulation. Now, earthquakes are often discussed in magnitude and intensity. Oftentimes you hear in the news reports that an earthquake of magnitude 7.3 occurred. Well, magnitude is a reflection of the total energy released by an earthquake, whereas intensity is more of a reflection of its impact on human culture, human structures. So the Mercalli intensity scale is oftentimes, or not often, discussed in news reports of earthquakes, but it is important. And you can see how you go from one, which is not felt, except by very few under very few favorable circumstances, to a Mercalli index of 12, which is total damage. You actually see surface waves on the ground. Objects are thrown upward in the air, and that has occurred in a few points in time in the Earth's human history, recorded history. Now, calculating a Richter magnitude or a magnitude on the Richter scale is a little bit different. The energy released at the earthquake point diminishes as it radiates outward, that's for sure. And so at any point in time, a seismogram can be used to calculate a Richter magnitude by knowing the distance from the earthquake, or the S&P travel time difference, SP wave, or the S wave, P wave travel time difference. It calculates a magnitude by looking at the amplitude of the actual wave, S waves, as they come through. Looking at 2 different earthquakes in Earth history, the 1906 San Francisco earthquake, a famous one, as well as the 1989 Loma Prieta quake that destroyed the Bay Bridge and caused extensive damage. Looking at the Mercalli index, you can see that the effect of the 1906 was felt in a much wider area. Almost all of California had at least a Mercalli index of 2 or 3. And the Mercalli index of 9 or 10, which is extensive damage, occurred up and down the coast. Whereas the Loma Prieta was definitely in the south. That's not really South Bay. I guess it kind of is South Bay if you know San Francisco. I guess that's South Bay. I don't really know. Anyway, not important. But it was. You notice how much more confined this quake was. Also extensive damage, but not as broadly extensive as in the 1906. Loma Prieta on the magnitude scale was a 6.9, give or take, whereas the San Francisco 1906 was up in the upper sevens, 7.8 maybe, I think. And so therefore, every step up in Richter magnitude is actually a step up in energy released of a factor of 10. So it's an exponential scale. So 10 times more energy was released in this one at 7.8 than was in this one at 6.9. And that's clear from the Mercalli index scale map here. This graphic shows the number of earthquakes per year of varying intensities. You can see there's almost 1 million earthquakes per year down at the low intensity of 2. You don't really even feel those. Very, very minor. They're rarely felt by humans down here. They can be similar to a moderate lightning bolt that shakes the earth. A large lightning bolt, on the other hand, has an intensity of, as it vibrates the earth, has an intensity upwards of 3. Also minor earthquakes, lots of them occurring, 100,000 to 10,000 per year. The really, really large, lots of damage, high damage earthquakes up abovewards of, magnitude 7, in between 20 and 1 per year. And humongous kind of catastrophic earthquakes are much, much fewer than 1 per year. Notice here the world's largest nuclear test. It was an 8.1 magnitude and wasn't even as large as the New Madrid in continental United States, kind of an interior continental earthquake, as well as the Chile in 2010 and Alaska in 1964. This graphic shows where you see the majority of magnitude 5, that is large earthquakes, over a period of 10 years. Remember, magnitude 5 quakes don't really occur very often, 1,500 to 150, somewhere in 1,000 to 100 per year. So looking at them over a 10-year average is quite illuminating. What do you notice about the location of these earthquakes? Does it look like anything, any map you've seen before? If you're thinking that it looks a lot like the map of the various tectonic plates on the surface of the Earth, you're exactly right. The earthquake patterns run right down the mid-Atlantic ridge, but where they're really dramatic are in the Ring of Fire. Japan Trench, Kermadec, Peru-Chile Trench, Aleutian Trench, mostly in areas of dramatic or intense continental ocean subduction. You see a lot up in the Alpine Himalayan belt, or Himalayan belt, however you pronounce it, and those are due to continental collisions on the tectonic scales. Tsunamis are what a lot of people also associate with earthquakes, and they are quite important. When you have an earthquake that occurs in an oceanic plate, you get large blocks of crust that will slide past each other. And what that can do is that can actually push a large volume of water. In this case, this movement of this block up actually pushes all this water up. The water doesn't really compensate well. Water is a non-compressible fluid, and so it basically, that energy of this large area of crust pushing up, pushes it up and causes a swell. A very, very large swell. If you imagine large areas of crust pushing a block of water, essentially, you can create a large disturbance in the surface. And when that large disturbance in the surface starts to relax and radiate out, what that can do is, this is a large volume of water, as it gets closer to shore. And you have to think about all the water underneath it as well. It's not just this little bit right here. It's all this water underneath. Moves up towards shore and has to fit from the bottom to where its equilibrium point is at the top of the wave, and you get this massive but relatively low height surge of water that is traveling very, very fast and has immense destructive power. Tsunamis have travel times just like earthquake waves as they radiate out from the point of origin, and energy of those waves dissipates as you move radially outward. So the closer a shoreline is to a tsunami-causing earthquake, the more damage, the more energy is released and is contained in that wave. The further far you go, those waves dissipate. So an earthquake in the center of the Pacific Ocean, for example, would impact Honolulu, Hawaii dramatically, and the Aleutians dramatically. By the time it reached Indonesia or South America, it would be quite dissipated, most likely. It's just a view of some notable earthquakes throughout history, organized by magnitude. You'll notice some of these don't have a magnitude number, but the estimate of deaths and comments indicate what scientists think it to be in terms of intensity, where it would fall in this intensity scale. Say China and Lisbon, Portugal in the 18th century and 16th century were massive. Charleston, South Carolina, 1886, is interesting because it's on the eastern United States. It does not fit with our typical view of where earthquakes can occur. So the New Madrid fault right in here and the Charleston earthquake over here are continental interiors. Those are really anomalous quakes. But you'll see Alaska, southern Chile 9.5, Alaska 9.2. These are massive, massive quakes. So I misspoke when I said this was organized by intensity. It's actually organized by year. Okay, but the largest one in recorded is southern Chile in 1960. The Alaska 1964 was a close second. One of the ways that scientists, or one of the efforts that scientists are currently working really hard at, is to try to predict earthquakes. And you can do it not in kind of monitoring earth tremors ahead of time, but the best way, or so far what seems to be the best approach, is to look for the statistical or the historical record of earthquakes and find areas where it makes sense for there to be earthquake seismicity, but where earthquakes haven't happened in a while. And that would imply that energy is stored up. So in this area we've had of the Sundra megathrust, which is near the Indian and Himalayan continental collision. You see lots of large magnitude earthquakes happening in the last 14, 15 years since the year 2000. And then the black areas represent large earthquakes that have occurred 1905 to 1999. Now, the white areas indicate areas where there have not been any earthquake foci mapped. And that implies that all the stress and strain that must be building up in those areas has not yet been released. Those areas would be very susceptible to future earthquakes. And resources can be concentrated there in preparation for those disasters, which you can't actually predict on a day-to-day basis, but you can plan ahead based on what has happened in the past and what the strain level may be at the present. This is just an example of the of that Himalayan collision area and the aftermath of a large, massive Pakistan or the large earthquake that occurred in Pakistan a few years back. Shows you the sketch of how the Indian plate is colliding with the Himalaya, the oceanic plate. It's subducting and eventually will subduct all the way, but this is creating a lot of stress and strain in this region right along here. And looking back at the last slide, we can see this magnitude 7.6 that occurred in 2005 released a lot of strain, but there are still zones where there is a lot of strain still presumably building up along this thrust. Now, one of the most interesting things that earthquakes can be used for, earthquake waves can be used for, is actually to map the interior of the solid Earth. In fact, scientists have not made direct measurements of the material nor of the structure of the solid Earth because it's essentially at this point, or heretofore, been impossible to get down that far. Nobody can drill. It's massive distances. So all the information that we have about the solid Earth is really inferred from different sources, but primarily from earthquakes. And that has to do with the fact that P waves and S waves are able to travel differently through different materials, and in fact S waves are unable to travel through a liquid at all. You'll notice there's a lack of S waves moving through here. Well, what's also interesting is that with wave refraction, if an earthquake is right here, there's P waves are moving through, can move through the liquid outer core, but due to refraction, there's this zone right around here. It's called the shadow zone. And the shadow zone is a phenomenon that's been observed, that earthquake waves are not seen for about 140 degrees on the opposite side of the Earth from a major earthquake. And science has been able to use that fact to infer that, in fact, the outer core is liquid. Because if it was solid, you wouldn't get as dramatic a refraction of these waves as they move through. The layered structure of the Earth has been determined by measuring earthquake waves as they travel through. Travel times are impacted by material composition, chemistry, as well as temperature and pressure. And the nature of the waves as they travel through are able to, or allow scientists to define zones of the interior solid Earth as liquid, partial melt, and solid. In fact, many scientists do what's called crustal or deep crustal or mantle tomography. It's much like a CAT scan or a CT scan in the hospital that use the movement of electromagnetic radiation in a CT scan to map density structure of a human body in a CT scan, or a human brain in a CT scan. Earthquake scientists, seismologists, can use the same type of approach. They can look for earthquakes around the world, large ones typically, and if they position seismometers and seismographs around the Earth at distinct and strategic locations, they can measure these waves as they propagate through the Earth. They can look closely at the fine structure of those wave arrivals and the modifications that take place to those waves, either due to reflection or refraction, and make much more defined insights into the structure of various areas. That about wraps it up for Chapter 8. It's a quick one. I hope you enjoyed this, and I'll move. Chapter 9 will be next, volcanoes, and we'll see you in the next lecture.